Alright, so we're going to go through multivariate regression and feature normalization in this notebook. So previously we've trained linear models, that is models that represent a straight line function. And that's because we were using some fake data which we knew had at least close to some straight line input-output relationship. But if the input-output relationship of our data is actually not linear, then they won't be able to fit that relationship. So if we just run the cell, we create some polynomial data now, not straight line, but in this case it's cubic by default. And this is some function which we've sampled from that. So now we can see that we're not going to be able to fit this with a straight line. So now if we try that, this is just stuff we've done before. This is the best fit, but it's not a good enough fit. It doesn't have the capacity to represent the cubic or quadratic looking nature of our actual data. So we need to be able to find a way to model more complex functions. And so for that, we're going to need to use a more complex model. So for example, this is the simple linear model we've used before, where we just have one weight with a single scalar input, multiply those two together, and then add some bias, some offset. But what we could use instead would be a higher order polynomial model, something like that looks like this, where it not only has the input, just the raw input x as the feature, but it also takes in that value squared, that value cubed, and it could take higher orders, and it has different new associated weights for each of those polynomial features. And those weights, again, they just compare, they just specify how much each of these different features should contribute to the output, which is our prediction there. So yeah, we could either have our model still just be a function of x, and then within the model we could raise to those powers, or instead we could augment the data set to include polynomial terms. And actually the latter, that one, is what we're going to do. And the reason for this is because we don't have to raise the input to any power when we actually make a prediction. That's all done in pre-processing. So we're just going to pre-process the data to augment it to include polynomial, that is higher order terms of the original input x. So the data set's going to include every example which has not just an x now, but an augmented x squared, x cubed, and maybe higher orders of x. And so now, instead of each of these individual examples being just a single number, they have several features. So in this case, we've got n different features in this example, x1. So the superscript which is the index of the example. So x superscript 2 is example 2. This is example 1, which has 1 to n features. And so in this case, n would be 3, and these different features would actually be the original x1 raised to different powers. So x12 would actually just be x11 squared, and x13 would be x11 cubed. So we're just going to take the single value features that we had before for our original data set and raise them different powers, and then for each example we're going to have those inputs raised to that power as additional features for that example. Cool. So now our data set is size m, the number of examples, by n, the number of features, and the number of features is the number of different orders of x which we're going to use. And this is one way that we could make a more complex model. So now it has the capacity to represent quadratic relationships, cubic relationships, and so on. And we're going to do the same thing as we did before, regression, but now we're going to do it with multiple variables, and we call this multivariate regression. The model is still linear. It's linear in the inputs which it takes in. So yes, it can represent cubic functions, but the prediction it makes is actually just a linear combination of those inputs, which might be a cubic order, so our input raised to the power 3. So Yeah, so it's multivariate in the fact that it's now finding coefficients for multiple variables. It's linear because it's still just a linear combination of those input features, which might be cubic or quadratic or whatever, and it's still regression because we're trying to predict a continuous output. So now we need more than one weight because we have more than one feature, so we need different weightings. We need different weights which specify how important is the associated feature to the output, how much does it contribute. So if it contributes a lot, the associated weight is going to be large. It could contribute a lot in a positive or negative direction, the weight will be positive or negative, or it could contribute not very much and maybe the weight's near zero. So if we had a perfectly cubic function we wanted to model, then it would have 0 weight for the x term, 0 weight for the x squared term, and 1 weight for the x cubed term. So we're going to use the same model. It's basically it looks exactly the same, except for this w now is a vector and this x is also a vector, although it looks the same. So we're just going to take a linear combination, a weighted sum of these input x, weighted by their corresponding weights in that vector. So this x is m by n, and this weight is n by 1. So the product of those gives you an n by 1 vector, and that's because we're going to make m predictions. We're going to have our y hat is also going to be that shape, m by 1, and this we still just have this bias, but that's just a single number, and we add that to every prediction. So yeah, that's a scalar. Okay, so now the so now we also have a slight change in our in computing the gradient of the loss function, because we have to do that for every different weight, and that's where this index j comes from. But for each of those weights, it's exactly the same as if we just had a single weight beforehand. So now we're going to need to change just a few things in our model class to make it not just linear hypothesis, but a multivariable linear hypothesis. So we are going to have to initialize not just a single random feature, but we're going to have to tell it we want it to have this size. So by default, it will just give us a scalar, a single number, but we actually want n features. We want that many different weights, because we're going to initialize this model and pass it an argument which tells it how many features does the data set have. So for each of those features, each of those different orders, in the case of our polynomial model, we're going to need to have an associated weight. Now we're going to need to make a prediction, and we can't just do self.w multiplied by x now, because self.w is a vector. So what we're going to need to do instead is np.matrix multiplication between our x and our weights. So like I said, just up here, our x is of size m, number of examples, by n, number of features, and the weights are of size n. So we've got m by n by 1, and that's going to give us an m by 1 sized output. So that's m examples and 1 value for each of them, because we're still predicting a single value. And then to each of those, we're going to add the bias on like that. Cool. And so there's a slight difference in the gradient calculation as well. So as before, we're trying to implement this equation. So we're going to do np.sum diffs multiplied by x. Okay, I think that's what we had before. So is that going to work? We'll see in a sec. And okay, yeah, so we're also going to have this function which takes in our inputs x and then adds to them the different order polynomials. So we'll just start with a vector of the individual x values, and then we'll augment augment our inputs by adding x squared, x cubed, and so on, to add different order polynomials to that data set. So to start with, we'll just change x from a vector into a m by 1 matrix. So it was a vector of just size m before. Then we'll initialize the new data set as x. So the new data set just starts off as that single vector of x's to start. And then we'll say for power in range from not 1 but 2 up to the order that we want to raise these to, plus 1. See where this is going in a sec. Then we will do numpy append to the new data set x to the power. Okay. So yeah, basically we're gonna go. So we have our input x, which is x to the 1, and then we want to go from. This is why I've started it from 2, because we want to add the x squared term next, not another x1 term. And then we want to go all the way up to, so say if we've got, if we want to go to order 3, well, this range, what it does is it iterates over this value up to everything until 1 before this value, which is why we add the plus 1 there. If we did it from 2 to 3, then it would just do the value 2. But we're going to do it from 2 to 4, which means it's going to do 2 and 3. It's going to give those as different powers as it iterates through this twice. So we're going to get the data set, which is originally x. Then we're going to raise x to the first power, which is 2 squared. And we're going to append that to this new data set. And in which direction? Well, which direction, which values that we want to change? We want to change the value of the number of columns, which is 1. So rows would be 0, columns is 0. Columns is what we want to change here. We're going to add different columns to this. And then we should print the new data set, which should be of size m by order now. Okay. So and then down here, we'll initialize our class like that, and that needs to know the number of features it has. So I've defined that in the line above. And then we'll create our polynomial inputs by calling this function. They both have extremely long names. And it takes in our x, and it takes in the order, which is going to be n features. Then we'll make predictions and we'll calculate the derivatives. Let's see if that works. Okay, cool. So diff is not defined. Yeah, diffs there, but that wasn't the error I was hoping for. I was hoping for this error. So these two shapes cannot be broadcast together with these two sizes. Why? Because one of them, and that's in this line here, where we're trying to calculate the rate of change of loss with respect to our weights. That's because one of them is a vector and one of them is a matrix. So this is why originally I commented this line out, because we do need to change something slightly here. We need to change our x into not our x, is it? We need to change our diffs. We need to reshape that into of size m by 1, and then that should run. And okay, now what have we got? Well, is this quite right? Because we're trying to calculate the rate of change of our loss with respect to our weights, but we got 3 weights. So we should have, and they're all going to affect the loss in different ways. So there should be 3 different values for this calc derivs, which is what we're printing here. This is the output. So yes, so basically what's happened here is we've done np.sum, and it's taken this, which we want to be a vector, and it's just summed it all up. So what we wanted to do was sum it up for all of the different examples. So sum it up over the direction which it has m, and so the size of this, we want it to be a vector of 3 for 3 different values for 3 different updates, for 3 different basically updates of which define how the loss changes with respect to each of those different weights, which we have 3. So what we need to specify here is that we don't want you to sum the whole matrix, we just want you to sum along the rows. So then we should print that, and now you see that the DLDW, which is what this last line returns to our output, is now a vector of 3. And so this is how our loss changes with respect to each of these, each of the associated weights. And this is how our loss changes as we change the bias by 1 unit. Cool, so we've done that now. Seems to be good. So now we should be able to run this, and there we have it. We've managed to model a more complex function which is not linear with using a polynomial model. So in this case, we're using a polynomial which includes terms up to x to the 4. Let's try it with squared. Looks like it can do that. But then if we try it with 1, it can't do it, and that's what we had originally when trying to fit a linear model. So we'll leave it as that. Seems to be a good job. Now we're going to talk about data normalization. So let's just go through some examples of trying to train these different kind of models. So now I'm going to run a very similar thing to what I just run before, but it's not going to work. And what's going to happen is it's going to say the weights after training, they've gone to nan. That is not a number. Okay, so what's happening is it's not converging. So maybe our learning rate is too high. Let's try and change that. I've set the learning rate to much lower. We'll run that, and you can see it's not getting it right. Like, it's what's happening. Something's not okay. So it does seem to converge to these values, so it doesn't explode. We don't get crazy predictions which are infinity or anything. It does seem to go to something, but it's not getting there fast enough by the looks of things. But we've already made our learning rate super small. So what's happening? Maybe our model doesn't have the capacity to represent the input-output relationship that we want. But I mean, actually, the data that I've made here is linear. So this is the order. It just is linear. So, and we're using a cubic polynomial, so it does have the capacity to represent this linear function. What's happening? Well, maybe we could try training it longer, but we can't increase the learning rate because otherwise it doesn't seem to converge. Try that. Yeah, it's going ridiculous. So it's almost getting there, but we can't make it go any faster. We're going to need to train it for way more epochs, but we don't want to do that because it shouldn't need to. We've already managed to train this one up here in less epochs with a much higher learning rate. Yeah, so we're doing this for the same number of epochs, but it's not converging. Why is this? Well, the change which I made here was that I sampled our polynomial data in the range from plus to minus 10, not from plus to minus 1 as is default. So it goes from minus 10 to 10 here. Now, basically, if we look at the derivative of our loss with respect to each weight, you can see that they are all multiplied by the input, the associated input for that index. So the weight corresponding to the cubic term is going to be multiplied by the weight by the cubic term. So x superscript j is actually x cubed in our data set. So we see that all the derivatives are proportional to the input. So this means that that the step size for each of those inputs is going to be proportional to that value. And if we go from minus 10 to 10 and we're including cubic inputs, well then the cube of 10 is 1,000. The square of 10 is 100, but but 10 to the power of 1 is just on the 10. So what we have is all our features are on drastically different orders of magnitude, and this means that the updates for each of them are going to be on drastically different orders of magnitude. So and that's basically what I've showed here. So our data set consists of x to the 1, x squared, x cubed, and so the inputs are proportional to, they're in the order of tens, hundreds, and thousands. And so what we have is all the gradients are on different orders of magnitude. Okay, so just read this if I need to mention anything. Okay, cool. So what we need to do, so yeah, one thing we could do is we could have different learning rates for each of the different parameters, and this basically, so it mean like, okay, the x cubed, the rate of change of the loss with respect to the cube weight is huge, so we'll have like a much smaller learning rate for that, so that those huge step sizes are made much smaller, and so that it converges in that direction. And then maybe the x terms, then they're not so large, so they don't need as small of a learning rate. But actually, This is a problem because soon we'll start using models which don't just have 3 parameters, but they have many different weights, millions of different weights. And so we don't want to have to figure out and hand tune these learning rates for each of those. So what we can do instead is something called feature normalization. And so, basically, well, let me just run this cell and then we'll see a visualization if something's happening. So this is our loss surface and a visualization of the optimization. So this is for basically the best learning rate that I could find. And so this one, it doesn't move smoothly down one side. It does jump from side to side, but it actually does diverge. It does converge. It does go towards the optimal value. Okay, so every time I run this, it crashes my kernel as well, so I need to restart it every single time. So now we can try. Let's try a different learning rate. Oh, I should have showed the other ones first, but okay. So let's run this cell. We'll see this. Okay, what's happening now? Now the learning rate is way too large, and it's diverged in this direction, which represents the coefficient of the x cubed term. So you can see that this loss surface, it changes much more drastically as we change x cubed, but not as we change x squared. You can see there is a minimum of x squared here, but it's a very shallow gradient in this direction and a very high relative gradient in the x cubed direction. So because we're using gradient descent, the size of the steps are proportional to the gradient. Well, in the x cubed term, they're going to take huge steps. And so you can see that it totally diverges in the x cubed direction, even though it actually does converge in the x squared direction. It does, the final values do actually go towards this minimum in the x squared direction, but the x cubed, they just go crazy. So so that learning rate's too high. Let's try again. Oh no. We need to okay, let's just forget that. Restart cell, run all above, uncomment this. This one should be better. So the learning rate was too large. Well, let's make it a lot smaller. See what can happen now. Now I've made it much smaller. In fact, I've made it way too small, or at least it's converged pretty quickly in the x cubed direction, but it's taking ages to make progress in the x squared direction, and that's because the learning rate, we've had to make it much smaller so that it does converge in the x cubed direction. But now it's way too small to actually make significant progress in the x squared direction because these gradients are really small. So if we have a small learning rate, we're going to multiply the gradient by a small number to produce the step size, which is going to be tiny. So you can see it's barely even moving forward at all now in the x squared term. And this is why, even though it does converge to some value, after some time we have to say, okay, cool, it should be done by now, but it's still not done because the step sizes are so small. So what can we do about it? We can use a technique called normalization or standardization. And this is basically what we do to try and put all of the inputs on the same order of magnitude so that the gradients are also on the same order of magnitude. So one method to do that is normalization, which is where we subtract the mean of each feature. So we go for each different feature, we subtract its mean and divide by its standard deviation. And this should center it around 0. So even if all these features, maybe they're like all nearby 100, normalization will center them all around 0 and have them have a kind of a unit spread. So they won't be extremely spread out or extremely tight together. They'll be spread out. They'll have a standard deviation of 1. Similarly, we could use standardization, which is where we subtract the minimum and divide by the range. So this puts all of our inputs on between 0 and 1. Two different techniques that you can use to do feature normalization or standardization. So what does that actually do to the data? Before normalization, our loss surface looked something like this, where we had very rapidly changing gradients in this direction, and actually much lower gradients in this direction, and this meant that we could make progress. We'd make rapid progress in the direction where the gradients are high, but not much at all in the direction where the gradients are much lower. What normalization does is it puts all of the features on the same order of magnitude, and hence all of the gradients on the same order of magnitude. So it changes our loss surface from looking like a valley into looking like a bowl like this. And so this makes convergence much easier because we can take the same size steps in each different direction. And so, yeah, we also have to, if we standardize our inputs, we also have to standardize any other inputs that go into this model, whether they're in the real world or for further training or for testing. We have to do the same thing to all of them. So we'll have to keep our, we'll have to keep the parameters of our normalization. So either the feature means and the feature standard deviations, or the feature minimums and the ranges. We'll have to store them and apply them to any new inputs which come in. How can we actually do that? Let's fill in this function to normalize the data. So we can use np.mean, simple as that, to get the mean of the data set. And the data set is m by n, so number of examples. Well, that's the number of examples. We want to calculate the mean of each feature. So there's n different features, but we want to calculate the mean over the examples. So we're going to collapse all the different examples to get a mean for all of them. So the axis that we want to change is the rows, so axis equals 0. We can also do the same for standard deviation, simple as standard deviation from NumPy, data set, and then axis equals 0. And so in this case, yeah, we're implementing normalization. So we've got the mean and standard deviation. You could just do the same thing with the min and the range. Then to actually normalize it, what we do data set minus mean divided by standard deviation. Let's run that. Cool. Kernel was crashed again because of that visualization. Come down here. We'll define that function. And now we should be able to train polynomials of much higher order. Okay, so here I'm going to set this to a 20 order polynomial. It's going to include terms up to x to the 20, and the only thing we're going to have to change is we're going to have to normalize our data set. So we're going to have to say, we're going to use this normalize data function, which we just wrote. We're going to apply that to our polynomially augmented inputs, and so yeah, these include all of the terms of x up to x to the power of 20, and then we're going to normalize all of them to put them to center them around 0 and give them standard deviation of 1. Should be able to train that and see that even with an extremely high order polynomial, we're still able to get a decent fit for this data. And yet we need to apply the same normalization or standardization techniques to any new examples which are model processes, whether they're for further training, testing, or real-world deployment. And that's it, we've done it. So you should now understand how to extend the idea between monovariate regression to the case where we have more than one feature to perform multivariate regression. And you should also understand how to normalize your features to prevent your model from either failing to converge or taking too long to do so. And you should also understand why we need to normalize unseen examples when we want to make predictions in the real world.